All right, now as the next topic, we want to look at the Laplace transform of integrals. Laplace transform of integrals. So far we calculated Laplace transform of derivatives. Now we want to look at Laplace transform of antiderivatives or integrals. So let's remind ourselves from Math 114 that how can we write an antiderivative for a given function? So recall from Math 114. So we saw in Math 114 that if f of t is a continuous function, then this function called area function, integral 0 to t f of, let's say, tau d tau, is differentiable and d to dt of 0 to t f of tau d tau is equal to f of t. In other words, this function, this area function, is an antiderivative for f of t. So this is called area function because it sweeps the area from 0 to t for the area enclosed by the graph of f and the x-axis. The net signed area, basically, from 0 to t. Now this function, which is called area function, is an antiderivative of f, meaning that if you differentiate this function, first of all, this function is differentiable, and if you differentiate this function, then you get f of t. So in this sense, this is an antiderivative for f of t. So this is called FTC part 1. Fundamental theorem of calculus part 1 exactly says this. It says that if f is continuous, this area function is differentiable and is an antiderivative for the original function. Now here, our goal is to compute the Laplace transform of this antiderivative function. Laplace transform of this function, integral 0 to t f of tau d tau. How can I calculate the Laplace transform of this antiderivative function? Let's apply the definition of Laplace transform. We know how the Laplace transform is defined: integral 0 to infinity e to power minus st f of t dt. So let's apply the definition. Laplace transform, integral 0 to t f of tau d tau is equal to integral 0 to infinity e to power minus st integral 0 to t f of tau d tau, then dt. So basically, this is, if you call it g of t, then Laplace transform is e to power minus st g of t dt. And this is my g of t here. So e to power minus st g of t dt. Now, how can I simplify the right-hand side? Now, if I call this one, this quantity, if I set it as u, So set or define u as integral 0 to t f of tau d tau. Then what will be du? Well, we know that du is u prime dt. Differential. This is the definition of differential. We learned in math 113 that dy is y prime dx. Now here my independent variable is t, so du is u prime dt. Now what is u prime? Derivative of this function here. What is derivative of this function? We just mentioned here. Derivative of this function is f of t, which is guaranteed by, as we said, FTC part 1. So u prime here is f of t. I can replace u prime with f of t. So du will be f of t dt. U prime equals f of t, c above. So if I call this part u, du will be f of t dt. So now I want to apply integration by parts. In order to calculate this integral, I want to apply integration by parts. So to calculate integral 0 to infinity e to power minus st integral 0 to t f of tau d tau dt, use the integration by parts. So this part I am calling it as u, and then the rest will be automatically dv. So we will write this integral as integral u dv. So this is u, and whatever that is left will be my dv. This is u, whatever that's left will be dv. So dv will be e to power minus st dt. If dv is e to power minus st dt, v will be integral of this, which is going to be e to power minus st divided by minus s. Antiderivative of e to power minus st will be e to power minus st over minus s. So now what do we know? We know that using integral u dv, we know that is uv minus integral v du. The integral above can be written as, how can I write the integral above? I know integral u dv is uv minus integral v du. So what is u, what is v, and what is du, what is dv? This part I called it u, whatever that is left I call it dv. So if dv is this, v will be this. And if u is this, du will be, according to our calculation, f of t dt. So I have u, which is this, I have v, which is this, I have dv, which is this, and I have du, which is this. I have everything ready. So integral above can be written as uv minus integral v du. U means integral 0 to t f of tau d tau. So this is basically Laplace transform of, when I say integral above, I mean this integral, which is same as Laplace transform of integral 0 to t f of tau d tau. So Laplace transform integral 0 to t f of tau d tau can be written as uv. U is this v. What is v? E to power minus st divided by minus s from 0 to infinity. Because look at the integral is from 0 to infinity. Integral 0 to infinity u dv. So it's uv, again with the same limits, 0 to infinity, minus integral v du, minus integral v. What was v? E to power minus st over minus s. V du. What is du? We calculated f of t dt. Du is f of t dt. F of t. So I can now write this integral, this expression as integral 0 to t f of tau d tau times e to power minus st over minus s from 0 to infinity. Then this becomes minus e to power minus st over minus s. Minus cancels with minus, and s can be taken out. So plus 1 over s integral, and again the same limits as before. So integral 0 to infinity e to power minus st f of t dt. Well, this is obviously Laplace transform of f, original function f. And I will show that this term is 0. Once I show that this term is 0, then that means the final answer will be 1 over s times the Laplace transform f of t. So then this will be 1 over s Laplace transform f of t. So the formula is this: Laplace transform of antiderivative, which means integral 0 to t f of tau d tau is equal to 1 over s Laplace transform of original function f. And it just remains to show that that term is 0. The term that I claimed is 0. I just need to show that it is 0. So what is this? Integral 0 to t f of tau d tau times e to power minus s t divided by minus s from 0 to infinity. We just need to show that this is 0. But let's start with the left-hand side. Left-hand side means, when we say infinity, at infinity means the limit of this guy, limit of this expression as t goes to infinity. So this is equal to limit as t goes to infinity of integral 0 to t f of tau d tau e to power minus st divided by minus s. And then So this one, this guy at infinity minus this guy at 0. When we say at 0, we mean at t equals 0. Remember the variable here is t. These limits, see, look at these limits. Like the original integral here, original Laplace transform, when it says 0 to infinity, means t changes from 0 to infinity. But inside here, I have tau as well, and the limits of tau are 0 and t. But this 0 and infinity are related to t. Similarly, this 0 to infinity and all 0 to infinities that I have and are appeared here are related to t. So when we say this integral at infinity means as t goes to infinity, minus this integral at 0 means at t equals 0. So if I replace t with 0, then I'll have minus integral 0 to 0 f of tau d tau e to power minus s times 0 divided by minus s. I have to replace t with 0 because of this term here. This term at infinity minus this term at 0. But integral from 0 to 0 of any function is 0. Integral a to a of any function is 0. This term is 0 because of this property. You saw in math 114 that integral a to a of any function is 0. So integral 0 to 0 of this function is 0. So this term is 0. So I just need to show that this term is 0. So again, it remains to show that this term limit as t goes to infinity, integral 0 to t, f of tau d tau times e to power minus st divided by minus s is 0. I wanted to show the left-hand side is 0. I wrote left-hand side, this left-hand side as I wanted to show it 0. I wrote it as this term minus this term, but this term is 0 according to this property. So I just need to show that this term is 0. Now, how do I show that this term here or this limit here is 0? Well, the idea here is to apply squeezing theorem. So if I look at the absolute value of this function here and show that it's less than equal to some positive function. In other words, if I squeeze this function between two function, left side and right side, and show that the limit of left side and right side are 0 as t goes to infinity, then that means this limit exists and is 0. I'll squeeze this between two functions whose limits are 0 as t goes to infinity, and that means limit of the middle function exists and is 0. So to show this, we first look at absolute value of this function. F of tau d tau times e to power minus st divided by minus s. So the limit is over t, and this s is a constant. So if I show that limit of this guy times e to power minus t is 0, then this is just a constant. The limit of that function times minus 1 over s will be also 0 because it's just a constant. So let me ignore this constant for now. And let me just look at absolute value of this function times e to power minus st. What can I say about this? So an absolute value integral 0 to t f of tau d tau times e to power minus st. So this is same as absolute value of integral 0 to t f of tau d tau times e to power minus st. But because e to power minus st is positive, exponentials are always positive. So absolute value of product of two functions is product of absolute values, but absolute value of e to power minus st is same as e to power minus st because it's already positive. Now this one I can write it, I can say that this is less than or equal to integral 0 to t absolute value f of tau d tau times e to power minus st. So here I use the property from math 114 that was saying that integral, let's say a to b, absolute value integral a to b f of x dx is less than or equal to integral a to b absolute value f of x dx. So this is the property from math 114. Absolute value of integral of a function is less than or equal to integral of absolute value of that function. So here we said integral absolute value integral is less than or equal to integral absolute value. And now what do I know about f of t? I know that it's a function of exponential order. Remember, this was the assumption that we made in order to guarantee existence of Laplace transform for the original function f. So we know, or we are assuming that, recall that we assume that f of t is of exponential order. To guarantee existence of Laplace transform f of t. So what can we say? We can say that absolute value f of tau is less than or equal to m times e to power c tau for some constants m and c. So what can we say? We can say that this absolute value that we were looking at it, absolute value integral 0 to t f of tau d tau times e to power minus st. This will be less than or equal to integral 0 to t m e to power c tau. Because see this this term here, absolute value f of tau is less than or equal to m e to power c tau. And then times e to power minus st times e to power minus st dt. And there's d tau here. Sorry, this is f of tau d tau times e to power minus st. So the f of tau is less than or equal to this quantity, d tau, then e to power minus st. So this part here, I replace it with m e to power c tau. Then there is d tau, which I wrote it again, and then times e to power minus st, which I also wrote it again. So this is equal to m. M is a constant. I can take it out. e to power minus st can be also taken out because this integral is over tau. So e to power minus st can be also taken out. Integral 0 to t e to power c tau d tau. Now, what is antiderivative of e to power c tau? It's e to power c tau divided by c. I need to calculate this between 0 and t. So then this is equal to m e to power minus st times e to power ct divided by c minus 1 over c. And this is same as m e to power minus st over c times e to power ct minus 1. So I showed that the absolute value of this expression is less than or equal to this expression. So if let's say if I know that absolute value x less than or equal to a, so from pre-calculus, you know that this is same as saying that x between minus a to a. If a is positive, absolute value x less than a is same as x between minus a to a. So I can say that the integral itself 0 to t f of tau d tau times e to the power minus st is less than or equal to m over c e to the power minus st and times e to the power ct minus 1 and bigger than or equal to minus this expression. We show that absolute value, this is like my x. So absolute value x less than this expression. That means x between minus this expression and this expression. Now, if I take limit as t goes to infinity, what happens as t goes to infinity? Now, limit of this expression m over c e to the power minus st e to the power ct minus 1 as t goes to infinity will be m over c times limit e to the power c minus s times t minus e to the power minus st as t goes to infinity. Now, if I assume that s is bigger than c, assume s bigger than c bigger than 0. C I already know is bigger than 0. Now I assume that s is bigger than c. Then what happens? Then c minus s will be negative. If s bigger than c, c minus s will be negative. So this will be a negative constant times t. T goes to infinity. So negative constant times infinity will be negative infinity. E to the power negative infinity will be 0. This one will also e to the power negative infinity because s is positive and minus s will be negative. So this will be also minus infinity, e to the power minus infinity again 0. So then this will be 0 because e to the power minus infinity is 0. So here we made the assumption s bigger than c, but that's okay because, you know, even in the previous cases, even for existence of Laplace transform, even for simple functions such as 1 or 1 over such as 1 or just a polynomial like Laplace transform t or t squared. So we always assume s is bigger than 0. And if necessary, if we assume that s bigger than c for some constant c, that's still okay. So here we assume that s is bigger than c, and under this assumption, we'll have e to power minus infinity here, e to power minus infinity here, which are 0. So this limit will be 0. So limit of minus this term will be also 0. If the limit of this expression is 0, minus this expression will be also 0. So limit minus m over c e to power minus st e to power ct minus 1 t goes to infinity, also 0. Again, of course, for s bigger than c. So by squeezing theorem, what can we say? We can say that the function in the middle, limit of the function in the middle exists and is 0, because limit of the smaller function, bigger function, both of them are 0 as t goes to infinity. So limit of middle function also exists and is 0. Limit as t goes to infinity, 0 to t, f of tau d tau, e to power minus st exists and is 0. So this means the limit of this expression divided by minus s, because the expression that we originally needed was that expression divided by minus s. We showed that this limit is 0, so this expression divided by minus s, s is a constant, limit is over t, will be still 0. So limit 0 to t f of tau d tau e to power minus st divided by minus s as t goes to infinity, also 0, as desired. Remember, we already showed that it's going to be enough if I show that this limit is 0. And we already showed that this limit is 0. So we are done. So we showed that Laplace transform of integral 0 to tau f 0 to t f of tau d tau is equal to 1 over s Laplace transform of original function f. Let's look at an example. Find, let's say, inverse Laplace transform of 1 over s times s squared plus 1. So this was the function or the expression that was appeared in one of the examples we did today. We were trying to find inverse Laplace transform of this expression. If you remember, we used partial fractions. And we wrote this as 1 over s minus s over s squared plus 1. If you remember, we had it in one of the examples we did today. So we can do this in two different ways. So solution 1 is the solution that we already mentioned above. Use partial fractions. And then we can write 1 over s times s squared plus 1 as 1 over s minus s over s squared plus 1, which you can check that this is true. I explained earlier that you can write this as a over s plus bs plus c over s squared plus 1. Find ABC, or just guess that you can write this expression in this form. And then inverse Laplace transform 1 over s times s squared plus 1 will be inverse Laplace transform 1 over s minus inverse Laplace transform s over s squared plus 1. And then use the table. Table tells us Laplace transform 1 is 1 over s. So Laplace inverse Laplace 1 over s is 1 minus cos t. Because the table says Laplace cos t is this expression. So that means inverse Laplace transform this expression is cos t. This is solution 1. Now solution 2, we can use the formula above that we had here. So let me call this one, let's say 4 star. Use 4 star above. So 4 star says inverse Laplace transform 1 over s f of s is integral 0 to t f of tau theta, where f of s is Laplace transform f of t. So if you look at the formula for star, it says Laplace transform of this function is 1 over s f of s. So that means inverse Laplace transform of right side is left side. So here, what do I have? I have inverse Laplace transform of 1 over s times 1 over s squared plus 1. So according to this formula, I can write it as integral 0 to t f of tau theta, where Laplace transform f of t is this expression here, 1 over s squared plus 1. So that's what this formula tells me. Inverse Laplace transform 1 over s f of s is 0 to t f of t, small f of t. What is small f of t? Small f of t is a function whose Laplace transform is capital F of s. So here capital F of s is 1 over s squared plus 1. So this inverse Laplace transform can be written as 0 to t small f of tau theta. And what is small f? Is the function, small f is the function whose Laplace transform is capital F and capital F of s. What is it in this case? 1 over s squared plus 1. So what is small f of t then? Small f of t is inverse Laplace transform 1 over s squared plus 1, which I can use the table to find it. Table tells me that Laplace transform sine t is 1 over s squared plus 1. So that means inverse Laplace transform 1 over s squared plus 1 is sine t. So now substitute back. And then we get inverse Laplace transform 1 over s times 1 over s squared plus 1 is equal to integral 0 to t sine tau theta. I replace small f of t or small f of tau with sine tau. Now what is antiderivative of sine tau? Minus cos tau. Minus cos tau between 0 to t. So that's going to be minus cos t minus cos 0. And that's again 1 minus cos t. So both solutions naturally led to the same answer. All right, now as an application of this Laplace transform integrals, let's see how to solve integral equations. So an application is solving integral equations. Now, what is an integral equation? Well, we know what's the differential equation. Differential equation means an equation where derivatives of the function are appeared. Now, similarly, integral equation means an equation where integral of an unknown function is appeared. So for differential equation, derivatives of an unknown function are appeared, and the goal is to find that unknown function. For integral equation, integrals of an unknown function are appeared, and the goal is to find that unknown function. So an integral equation is an equation that includes the integral of an unknown function, and the goal is to find that unknown function. So for example, let's say if you have integral 0 to t, let's say f of tau d tau equals, for example, 16t squared minus t. So see, this is an equation. There is an unknown function f, and the goal is to find f, and the integral of this unknown function is included here. So this is an equation. It includes the integral of an unknown function. So this is an integral equation. Or another example, let's say integral 0 to t, let's say e to power tau, f of tau, d tau equals, for example, sine t minus t. So again, this is an equation, integral of, there's an integral of, not f itself, but f times a function. So it's still considered an integral equation because there is an unknown function and the integral is appeared. So still this is considered an integral equation, although integral of the function itself is not appeared. Instead, integral of a function, the unknown function times another function is appeared. So, but as long as you have an unknown function and integrals are appeared, it's called an integral equation. So now let's see how we can use Laplace transforms to solve an integral equation. So for example, use the Laplace transform to solve the following integral equation. So integral 0 to t f of tau d tau equals 5t cubed plus 2t. So this example asks us to solve this integral equation with Laplace transforms. So how can we use the Laplace transform? Like the previous examples for solving ODEs, for example, how do we use Laplace transform to solve an ODE? First, we applied Laplace transform to both sides of our equation. And then we did the remaining steps, simplifying and other things. So let's do the same thing here. So apply Laplace transform to both sides of the equation above. And what do I get? Laplace transform integral 0 to t f of tau d tau equals Laplace transform 5t cubed plus Laplace transform 2t. Remember, Laplace transform is linear, so Laplace transform addition of two functions is addition of Laplace transforms. And we also have a formula for Laplace transform of this antiderivative 0 to t f of tau d tau. We saw that this was a 1 over s f of s. This one resides 1 over s f of s. Laplace transform t cube. We know it's 3 factorial over s to power 4. Laplace transform t squared. We know it's 2 factorial over s to power 3, because Laplace transform t to power n is n factorial over s to power n plus 1. So this is 1 over s f of s equals 5 times, so 3 factor means 6. So 5 times 6 is 30. So 30 over s to power 4 plus 2 factor is 2 times another 2 here times this 2 will be 4. So 4 over, so this is 2t. 2t, so I need Laplace transform t here, not t squared. Laplace transform t, we know that it's 1 over s squared. Or 1 factorial over s squared, which is same as 1 over s squared. And then times 2 will be 2 over s squared. So then capital F of s will be, so this is 1 over s times f of s. So if I multiply both sides by s, f of s will be 30 over s cubed plus 2 over s. 30 over s cubed plus 2 over s. So this is capital F of s, which is same as Laplace transform f of t. So I'm looking for f of t. F of t will be inverse Laplace transform of capital F of s, which means inverse Laplace transform of 30 over s cubed plus 2 over s. Again, inverse Laplace transform is linear. I can write it as inverse Laplace transform 30 over s cubed plus inverse Laplace transform 2 over s. Now I can use the table. Table tells me that Laplace transform of t squared is 2 over s cubed. And Laplace transform 1 is 1 over s. So this is, instead of 2, if I had 2 over s cubed, then my function would be t squared. But this is, instead of 2 over s cubed, is 30 over s cubed, which means 15 times this. So in other words, you can write this one as 15 times 2 over s cubed. And then 15 can be taken out. So I can write this one as 15 Laplace transform 2 over s cubed. And this one, 2 can be taken out. 2 times inverse Laplace transform 1 over s. And inverse Laplace transform 2 over s cubed is t squared. Inverse Laplace transform 1 over s is 1. So 15 t squared plus 1. So this is the final answer. We got that f of t is 15 t squared plus 1. So we were given an integral equation, and the goal was to find the unknown function f of t. We found out that the unknown function f of t is 15t squared plus 1. I want to give a remark here, and that is the example above can be also solved without Laplace transforms. So if the question says use Laplace transforms to solve it, then you have to use it. But if it doesn't say use Laplace transform, it just says solve the equation, then you're allowed to use any method, whether Laplace transform or without Laplace transform. So how can I solve this without Laplace transform? Let's say if the question did not ask me to solve with Laplace transform, what other method could I have used to solve this equation? So look at this equation here. If I differentiate both sides, what do I get? So let me write down the equation one more time. Zero to t, f of tau d tau equals 15, say 5t cubed plus 2t. 5 2t. So now differentiate both sides. If I differentiate both sides, what do I get? So d to dt, 0 to t f of tau d tau equals d to dt of the function on the right side, which is 5t cubed plus 2t. Now by FTC, I know that FTC part 1, I know that, d to dt of 0 to t f of tau d tau is f of t. This is exactly what FTC part 1 tells us. You saw it in math 114. We also reminded today, just a few minutes ago, that this function is differentiable. As long as this function small f is continuous, this area function is differentiable, and derivative of this function is small f of t. So left-hand side can be replaced with f of t, and derivative of right-hand side is 15t squared plus 2t plus 2, which is the same answer as sorry, this one also 15t squared plus 2, because this was 2 times 1. 2 times 1 is 2. I had to write 2 here. 2 here. So whether we use Laplace transform or without Laplace transform, we got the same answer, 15t squared plus 2. Well, for this answer, it was easier to do it without Laplace transform, just using FTC. But in some examples or some problems, we really have to use Laplace transform, or at least it's easier to solve it with Laplace transforms. So it's important that you know about Laplace transform method and Laplace transform of integrals and how to use it to solve integral equations. Okay, guys, that's all for today. Thank you and see you next time.